the introduction. Okay, so today I'll introduce to you what I call the wonderful compactification of a Cartan subalgebra of a semisimple algebra. So this is based on joint work with Sam Evans. My plan for today is as follows. So part 1 would be background, and then part 2 will be relevant definitions and basic examples. And then part 3 will be explanation of geometric properties of Hbar. There's a question in the chat.
Sorry, it was not a question. I was just wondering if it was only me that I hear some echo after you talk, but if nobody...
I also hear some echo. So let's go back to the talk. So I'll work over the complex numbers. So in the general setting, I'll let U, pi U be a Poissonly group. The infinitesimal information of such an object is encoded in what is called a Manin triple. So it consists of the following things. So we first have this symbol here, which is usually called the Drinfeld double Lie algebra. This thing means that U acts on U star by the coadjoint action, and U star also acts on U by the coadjoint action. And then this Drinfeld double is equipped with an angle bracket, which is a symmetric, non-degenerate, invariant bilinear form. And then with respect to this form, we have two Lie subalgebras, U and U star. Both are Lagrangian with respect to angle bracket. And moreover, the Drinfeld double Lie algebra as a vector space is the direct sum of the two Lagrangian subalgebras. Okay, but this direct sum is not a direct sum of Lie algebras. Okay, so then with all of these, I can define the variety L of Lagrangian subalgebras of the Drinfeld double. So as I said, it consists just of Lagrangian subalgebras of the Drinfeld double Lie algebra. And then, of course, you can think of this as sitting inside the Grassmannian of d-mu dimensional subspaces of the Drinfeld double. And it's rather easy to see that it's a closed subvariety because being Lie subalgebra and being Lagrangian are both closed conditions. Okay, so then this is going to be called the variety of Lagrangian subalgebras of the Drinfeld double. Okay, so what is the significance of this? Well, so if M, pi M is a Poisson variety, and there's a transitive action of the group U on M, then we say that M, pi M is a Poisson homogeneous space for the Poissonly group U, pi U, if the action map is Poisson. Okay, just like for a group action, we have homogeneous spaces of that group. For an action of a Poissonly group on a Poisson manifold, we also have the notion of Poisson homogeneous spaces. Okay, so then when M is a Poisson homogeneous space, then we actually have a map from M to the variety L, which is usually called the Drinfeld map. What it does is it sends a point on small m to L sub m, which is all pairs x comma alpha inside the Drinfeld double, such that alpha restricted to the stabilizer in U of M is equal to 0, that way I can think of alpha as a covector on M at the point small m. Okay, once I have a covector, what I can do is I can insert it into the Poisson bivector field. So I insert alpha into pi m at small m. This is going to give me a vector at small m. The condition is that it's equal to x modulo the stabilizer in U at M. Okay, so this is the Greenfield map. It has various nice properties. For example, it's U equivariant. One can construct a Poisson structure on the variety of Lagrangian subalgebras so that the Greenfield map is Poisson. And up to a covering map, the Greenfield map is all embedding. Okay, so then you can find these results in the work of Greenfield and also Evans and Lu. All right, so then it makes sense to think of L as the universal Poisson homogeneous space, right? Because once you have a Poisson homogeneous space, you can embed it U equivariantly as a Poisson subvariety into L. Okay. So for that reason, it is important to understand algebra geometric and Poisson geometric properties of the variety of Lagrangian subalgebras. For example, it's important to understand its U orbits because these are Poisson homogeneous spaces. Okay, so are there any questions so far? All right, great. So for today, I'll be interested in the following special case. So fix a semisimple group G, I'll assume it's of adjoint type, and then German G is the Lie algebra of G, G star the dual space, and then G star together with addition is an algebraic group. Oh, sorry, there's a question. Is L in fact a Poisson? No, L is very large. Somehow you can think of it as a union of Poisson homogeneous spaces for U. Okay. All right. So on this algebraic group, we have the Kirillov-Colson-Poisson structure denoted by pi kk, making this group into a Poisson Lie group. And the Manin triple of this Poisson Lie group is as follows. So the Greenfield double Lie algebra is G semi-direct product G star, whose Lie algebra structure I'll explain later. And then the two Lie subalgebras are just G and G star, where G star is just a abelian Lie algebra, and angle bracket will also be explained later. Okay, and then by the construction above, I have a variety L of Lagrangian subalgebras of G semi-direct product G star. Okay, so our long-term goal is to understand algebraic and Poisson geometric properties of this variety L, by which I specifically mean, for example, to classify its G orbits, or to classify the orbits of the Greenfield double group, and also classify the symplectic leaps, etc. Okay. So for now, I'll remark that this question is quite hard. And the reason for that is, for example, we know that if you want to classify, let's say, G orbits in L, then more or less you would have to be able to classify all finite dimensional Lie algebras. Okay, which we know more or less is impossible. Okay, for today, my goal will be much smaller than this, I'll look at a closed subvariety of L, which is the wonderful compactification of a Cartan, and discuss various geometric properties. Okay. So what is this Drinfeld double Lie algebra? So I denote by German D, the Drinfeld double Lie algebra. Its Lie bracket is given like this. So x comma alpha bracket y comma beta is in the first component, you just take the usual Lie bracket in G. In the second component, you just look at the coadjoint action. And for the angle bracket, you just essentially write down the only possible formula. And then capital D is the Drinfeld double group. So group G semi-direct product with G star. And I wrote down the formula for multiplication. Again, it's the usual formula for a semi-direct product. Now with these formulas, it's not too hard to see that the Lie algebra of the group D is the Lie algebra German D. So we have an adjoint action of D on D. And as I remarked above, angle bracket on the Drinfeld double is invariant, by which I mean it's invariant under the adjoint action. So the adjoint action sends a Lagrangian subalgebra of D to a Lagrangian subalgebra of D. Okay, therefore we get an induced action of the group D on the variety L. And this action by abuse of notation is also denoted by AD. All right, so in this variety L, I have a distinguished point, namely the Lagrangian subalgebra G. Okay, remember as I remarked above, in the Drinfeld double, U and U star are both Lagrangian subalgebras. Okay, so in this case, I just look at G, and it's easy to compute its stabilizer inside D, which is the group G. So I can identify the D orbit through G with D modulo G. And remember, D is G semi-direct product G star. So I can identify D mod G with G star. Okay, and the map is, so alpha goes to the class of E comma alpha, and the corresponding Lagrangian subalgebra is just adjoint of E comma alpha acting on G. Okay, if you go back to the formula above for the adjoint action, you will see that this Lagrangian subalgebra is this. In other words, if you wish, you can think of this as the graph of the coadjoint action of alpha. All right, so then here comes the first important definition for today. I define G star bar to be the closure of the D orbit through G inside L. Okay, now remember L is a closed subvariety of the Grassmannian, so it's projective. So G star bar is also projective. Okay, and this is called the wonderful compactification of G star. Sorry, that's a typo. All right, the geometry of this G star bar is still quite mysterious. We don't understand much about it at this point. Okay, but what we do understand quite a lot about is the following. So I take H to be a Cartan subalgebra of G. I embed H into G star by the Killing form. So then I have an embedding of H into L, just this composition here. And if you follow all the definitions above, you will see that, so we first sends x to kappa of x comma blank. And then this goes to the graph of the coadjoint action of kappa of x comma blank. And then I identify G star with G via the killing form, and then I'll just write the second component as x bracket y. So here. Okay, so so after identifying G star with G, we see that an element x of H is sent to all pairs y comma x bracket y, namely the graph of the adjoint action of x. Okay, any questions so far? Okay, great. So this Hbar is, oh sorry, then I define Hbar to be the closure of H inside L. And this is to be called the wonderful compactification of H. Sorry, there's another question. So what is the wonderful compactification of SU2 star? Okay, so I'll explain the case of SL2 star. I mean, as I remarked above, I work over the complex numbers, but I believe for SL2 is essentially the same story as SL2. All right, so I'll come back to this later. Okay. All right, so just to be a bit more explicit, and maybe also explain a bit why Hbar is easier to understand than G star bar. So we let phi be the set of all roots, and for each root lambda, I choose a root vector E lambda. And then if you go back to this last line here, then it's not too hard to see that the embedding of H into L sends an element X of H to this Lagrangian subalgebra. Okay, so so if this element y here is in H, then x bracket y is equal to 0. That's why we get this first sum and H direct sum 0. And then if y is the root vector E lambda, then x bracket y is lambda x times E lambda. Okay, so so that's concretely what the image of x is. And this also explains why H bar is easier to understand than G star bar, because if this y is just a general element, if this x is a general element of G, then we won't have this nice presentation down here. Okay. Any questions so far? All right, great. Now just maybe a bit of digression, just to explain why I am interested in G star bar and H bar, or why did I define them the way I did? Okay, so recall that there's a standard Poisson Lie group. So G comma pi sub st. So this Poisson structure is obtained from the classical R matrix by left and right translations. Its bending triple is usually presented in this way as I wrote. The Drinfeld double Lie algebra is usually identified with the direct sum of G with itself. And then the two Lagrangian subalgebras are the diagonal Lie subalgebra and also the standard dual, where the standard dual is the anti-diagonal H plus and direct sum n minus. Okay, and then we have the variety of Lagrangian subalgebras of G direct sum G. Again, as above, the Drinfeld double group G cross G acts on it. Okay, now in this situation, the variety of Lagrangian subalgebras has a distinguished point G delta, the diagonally subalgebra. This is a replacement of our G. Okay, and the stabilizer inside the Drinfeld double group is just a diagonal group. So you can identify the orbits through G delta of the Drinfeld double group with G cross G modulo G delta, which I identify with G via the map G goes to E comma G. Okay, and then one can verify that the closure of this orbit inside the variety of Lagrangian subalgebras is the de Concini processi wonderful compactification of G. Okay, so completely analogy between our definition and this usual construction of the de Concini processi compactification of G bar, of G, sorry. Okay, and then if H is a Cartan subgroup, we can take the closure of H inside G bar or inside the variety of Lagrangian subalgebras. This H bar has the following nice properties. For example, it has a unique open H orbit, which is H equivariantly isomorphic to H, and it's also a normal variety. And then, well, if you are familiar with it, you will realize that this is a toric variety. Okay, and well, we know that each toric variety corresponds to some combinatorial data called a fan. The fan corresponding to H bar is just the Bell chambers. Okay, so this is one of the most important examples of toric varieties. All right, so then by the work of Evans and Lu, if you, for example, look at the closure of the orbits of the Drinfeld double group, what do you get? So you get a fibration over a product of two copies of partial flag varieties. So whatever the meaning of PS and PT minus are, they are just some parabolic subgroups. So the space here is just a product of two copies of partial flag varieties. And the fiber here, GS bar, where GS just means some semi-simple group, and GS bar means this wonderful compactification. Okay, so so then what this tells me is that if we would like to understand the geometry of L, and if we assume that we understand partial flag varieties quite well, then we need to understand wonderful compactifications of G. Okay, so then for the same reason, the hope is that in our situation, to understand the geometry of our variety of Lagrangian subalgebras, it helps to first understand the geometry of G star bar. Okay. All right, so are there any questions so far? Okay, great. So now I can answer the question of what is G star bar for G equals SL2. So if G is SL2, this is the computation. So and then G star, sorry, maybe I'll just write SL2 star bar can be identified with P3. Okay, this one can prove, but is not easy and it's not illuminating. So I'll maybe just give you the answer without explanation. What I'll do is I'll explain in great detail what H bar is. So for that purpose, let us observe the following. So if I go back to, yes, if I go back to this line here, I see that x in H is sent to this Lagrangian subalgebra, where the first summand is always fixed. It's always H direct sum 0. Okay, the only thing that depends on x is lambda of x, which is a coefficient of the second component. Okay, so then this tells me that the embedding of H into L factors through the following map. So I send H to C to the V plus. So this is a complex vector space having all positive roots as a basis. What I do is I just send x to the tuple lambda of x. Okay, and then from here, I get a map from, to the variety of Lagrangian subalgebras, where a tuple x sub lambda, well, as you expect, goes to H direct sum 0 plus the span of E lambda times X lambda E lambda, and also E negative lambda negative X lambda E negative lambda for all positive roots lambda. Okay, and then it's clear that this composition is the embedding of H into L, as we saw above. Okay, and then C to the V plus sits inside P1 to the V plus. You just compactify each coordinate. Okay, and it's rather clear that this, the embedding of of C to the V plus into L factors through P1 to the V plus. And this is a closed embedding. So H bar can also be understood as the closure of H inside P1 to the V plus. All right. So then I go back to my SL2 example. This time I have an embedding of H into C to the V plus, but this time V plus consists of one root. Okay, so then this is just an iso, and then V of C goes to P1. So H bar is a closure of C inside P1, namely it's just P1. And for some reason, I'll rewrite this as H disjoint union with infinity. Okay, and then if G is SL3, this time H sits inside C to the third power, right? Because this time we have three positive roots, alpha, beta, and alpha plus beta. Okay, so X goes to alpha X, beta X, and then alpha plus beta applied to X. And then C3 sits inside P1 to the third power. So then it's not too hard to verify that H bar is cut out by the multi-homogenization of the polynomial X alpha plus X beta minus X alpha plus beta, where of course X alpha, X beta, and X alpha plus beta are inhomogeneous coordinates on C3. Okay, and this so X alpha 1 times X beta 0 times X alpha plus beta 0 plus X plus X alpha 0, X beta 1, X alpha beta 0, and then minus X alpha 0, x beta 0, x alpha plus beta 1. Okay, then from here, let's analyze what H bar is. So the three coordinates, x alpha, x beta, x alpha plus beta, if they are all finite, then we are just in H. And if one of them is infinite, for example, x alpha is infinite, which means x alpha 0 is 0, and then this would force x beta 0 times x alpha plus beta 0 to be 0, namely either x beta or x alpha plus beta has to be infinity. Okay, so then we have infinity, infinity, or this is infinity and this is infinity, or this is infinity. And once we have two infinities from our defining equation, it's easy to see that the third component is free. So it could be anything in P1. Okay, so then this tells me that H bar is H disjoint union with 3 copies of P1. And the 3 copies of P1 correspond to alpha, beta, and alpha plus beta. Okay, is this clear? Okay, great. All right, so now let me give you some general geometric properties. So the first question I would like to answer is, what is the defining ideal of H bar inside P1 to the Phi plus? Okay, so naively, one would like to say the following. So from our SL2 and SL3 example, one might want to say, okay, so I first write a positive root as a linear combination of simple roots. In the SL3 example, we write alpha plus beta as alpha plus beta. Okay, and then this will give rise to a linear polynomial, as I wrote. And then I multi-homogenize this linear polynomial. And then I would expect that this cuts out H bar. Okay, but in general, this is not true, that these are two field equations. Okay, so maybe just an example. So if G is SL4, then H sits inside P1 to the 6th power, because this time we have 3 simple roots, alpha 1, alpha 2, alpha 3, and then 3 non-simple but positive roots. Okay, so I'll write it down. Alpha 1, alpha 2, alpha 3, alpha 1, 2, alpha 2, 3, and alpha 1, 3. Okay, and then naively, you would say the following. So I can write alpha 1, 2 as alpha 1 plus alpha 2, alpha 2, 3 as alpha 2 plus alpha 3, and alpha 1, 3 as alpha 1 plus alpha 2 plus alpha 3. Okay, and then if the inhomogeneous coordinates corresponding to these roots are x, y, z, maybe u, v, and s, and then naively, one expects that H bar is cut out by the multi-homogenization of, so the first relation alpha 1, 2 equals alpha 1 plus alpha 2 corresponds to x plus y minus u, the second one corresponds to y plus z minus v, and the last one corresponds to x plus y plus z minus s. Okay, but as you can verify this, these are not enough. So in fact, I also need, for example, so x plus v minus s. So this is alpha 1 plus alpha 2, 3 equals alpha 1, 3. Okay, I also need z plus u minus s. I also need x minus u minus v plus s. This is because alpha 1 plus alpha 1, 3 is alpha 1, 2 plus alpha 2, 3. Oh, sorry, not x, but y. Okay, so this example shows that the question of writing down generators of the defining ideal of Hbar is not as trivial as one thought about. So then what I do is as follows. So I'll introduce x lambda. So these are inhomogeneous coordinates on P1 to the P plus. And then for each linear relation, let's say C lambda times lambda equals 0 among the positive roots, I consider the linear polynomial summation C lambda times x lambda. And then I define an ideal, which I'll call I of phi. So this is ideal generated by the multi-homogenizations of all these linear polynomials. Okay, so whatever it is a multi-graded ideal of the polynomial ring C adjoint x lambda comma 0 x lambda comma 1 for all positive roots lambda. And of course, it's easy to see that the vanishing locus of this ideal contains Hbar, right? And now my first theorem for today is that the vanishing locus of this ideal is precisely Hbar. Okay, so what you have to do is you have to look at all linear relations satisfied by the positive roots. Okay, later if I have time, I'll maybe give you a smaller set of generators. All right. To describe geometry of Hbar in more details, I'll need to introduce some definitions. I'll let phi prime be a root system of phi. And then definition, phi prime is closed if whenever lambda and mu are inside phi prime and lambda plus mu is a root, we have lambda plus mu must be in phi prime. So it's closed under root addition. And then we say that phi prime is good. Yes, it's good if phi prime is maximal with respect to inclusion among all closed root subsystems of phi whose rank is rank phi minus 1. So good means maximal among closed co-rank 1 root subsystems. Okay, so examples. So if phi is of type A1, then any good root subsystem by definition is co-rank 1. So phi prime is of rank 0. So the only option is the empty root system. Okay, now if phi is of type A2, it's easy to verify for yourself that there are the following 3 possibilities for a good root subsystem, namely plus minus alpha, plus minus beta, and then plus minus alpha plus beta. Okay, now you might have noticed in type A1, I have only 1 good root subsystem. In type A2, I have 3 of them. If I go back to my example of Hbar, okay, in type A1, namely SL2, the boundary has 1 irreducible component. In type A2, namely SL3, the boundary has 3 irreducible components. Okay, and as I remarked, they correspond to alpha, beta, and alpha plus beta. And these are precisely the 3 good root subsystems. Okay, so this indicates that there's a one-to-one correspondence between irreducible components of the boundary of Hbar and good root subsystems of phi. Okay, and this is indeed the case. But to state the result in a rigorous way, let me first make some observations. Maybe not. Yes, okay, let me do it anyways. So if I have x lambda inside Hbar, which sits inside P1 to the P plus, then I can look at all lambda such that x lambda is finite. Okay, and you can try to convince yourself that these are positive roots of a closed root subsystem of phi. Okay, then to determine boundary components of Hbar, well, then we just need to look at the maximal closed root subsystems. Okay, so that's maybe one way to convince yourself why there's such a bijective correspondence. Okay, so so the notations. So if phi prime is good, I can choose G prime and H prime, where G prime is a semisimple Lie subalgebra of G, and H prime is a Cartan subalgebra of G prime, such that the root system of G prime comma H prime is phi prime. Okay, and from here, I have H prime bar, the wonderful compactification of this Cartan by our theorem 1. It is a vanishing locus of some ideal I of P prime, which sits inside P1 to the phi prime plus. Okay, but then I can make this sit inside P1 to the phi plus. I just so if some lambda is in phi but not in phi prime, I just put it to be infinity. Okay, so then this way I can think of H prime bar as a closed subvariety of P1 to the phi plus. All right, so then my second theorem for today is that H bar is H disjoint union with the union over all good root subsystems of H prime bar. So in particular, have a bijection from good root subsystems of phi to irreducible components of the boundary, which sends phi prime to H prime bar. Okay, any questions? All right, great. Okay, so now remember, so H with addition is an algebraic group, and it acts on H via translation. The section extends to an action of H on H bar, as you can easily verify. Now this H bar has the property that there's a unique open H orbit, right? Namely just the open part H. Okay. So now again, if you recall the definition of a toric variety, if I can prove that H bar is normal, then it's quite reasonable to regard H bar as an additive toric variety for the additive torus H. Right. So then my next goal is to show that H bar is indeed normal. So so theorem 3. So if I take H bar and I look at its regular locus, and then I know that this contains H and all phi prime good H prime. Okay, so the open part, of course, is smooth, but then for each of the boundary divisors, its open part is also smooth. Okay, so this means that the singular locus of H prime, of H bar is contained in the boundary of each of the H primes. Okay, so in particular, H bar is regular in codimension 1. Okay, and then theorem 4. This is a combination of a theorem of Ardila and Booker and our analysis of the structure of H bar. So I say that H bar is Cohen-Macaulay. In particular, it satisfies Serre's condition at S2. So as a corollary of theorem 3 and theorem 4, H bar is normal because it's R1 and S2. Now I'll remark what I said above. So now it is reasonable to regard Hbar as an additive toric variety. Okay, so I'm in the process of developing a general theory of additive toric varieties. Maybe just in case someone is interested, these varieties are closely related to hyperplane arrangements. So for each what is called a central and essential hyperplane arrangement, one can associate a additive toric variety. Okay, so from our theorems, we see that it's important to understand good root subsystems of phi. Okay, so I'll give you an algorithm of how to find them, and then I'll stop. So this is what I call the Borel-Dicey-Benzol algorithm. Theorem. This is theorem 5. So up to the action of the Bell group, good root subsystems of phi are obtained in the following way. Step 1, I take a connected component, let's call it D. Sorry, I used D for the Drinfeld double. No, sorry, I'll use C of the Jenkins diagram of, and then I affinize C to the affine Jenkins diagram C hat. Okay, remember in C hat, each node has what is called a Jenkins label. Right, so so the affine node has Jenkins label 1, and for each simple root, what you do is you write the highest root as a linear combination of the simple roots, and the Jenkins label of a simple root is the coefficient in this expression. Okay, so then the first step is remove 2 nodes whose Jenkins labels are co-prime. And then the last step is take the root subsystem generated by the remaining nodes. Okay, I guess I'll stop here. Thank you so much.